Good morning, everyone. Thank you for joining us on our first webinar back of the year. This is FailSafe features in the Horner controllers. The presentation's roughly about 20 minutes, and if you have any questions, feel free to put them at any point, and we'll get to those at the end.
Hello and welcome to today's webinar. Today we're going to talk about the FailSafe features in our Horner all-in-one controllers. Let's get started. Let's look at our agenda for today. We will explore the concept of FailSafe, delve into OCS memory architecture, and discuss two crucial FailSafe features: backup and restore, which is arguably the most significant, and autoload, which offers valuable capabilities. We will also look at cloning, which, while not a direct FailSafe feature, is closely related. There will be demonstrations throughout, and we'll finish with a Q&A session. FailSafe features comprise of a set of functionalities aimed at maintaining continuous machine operation and preventing program and memory disruptions. The most typical challenges a machine may encounter throughout its lifespan often relate to battery issues. Batteries have limited capacity, can be affected by temperature, and occasionally exhibit unpredictable behavior. Memory corruption, on the other hand, has become less frequent in recent times. The significance of fail-safe features increases as equipment ages, mainly due to battery degradation over time, resulting in lower capacity and increased susceptibility to failure. Now we'll look at OCS memory organization. In OCS all-in-one controllers, there are two primary types of memory. The first is RAM, which is fast memory typically used for variables or registers. It requires continuous power to retain data. RAM offers several advantages, including its speed and resistance to excessive write cycles. It's important to note that in a running application program, files can change rapidly, leading to frequent writes to RAM. The second type is flash memory, which is non-volatile and doesn't require continuous power to maintain memory. However, it's not as fast as RAM and can wear out when continuously written to. While flash memory offers the advantage of retaining data during power down events, it has limitations in terms of write speed and durability. Those are the two main memory types in the OCS. First, we'll look at what we refer to as our traditional architecture, which closely resembles how many PLCs have historically operated. In this conventional approach, we use battery-backed RAM for variables. This RAM, though fast and capable of rapid writing, relies on a battery to retain its memory when power is removed. The advantage here is the retention of memory. The drawback is the need for a battery, which depletes over time as the machine experiences power down periods. In the traditional architecture, the application program is traditionally stored in flash memory, which requires a relatively substantial battery to maintain RAM power over the machine's lifespan or several years of operation, considering occasional power down events. In the case of traditional architecture, specifically concerning the Horner all-in-one controllers, if you lose your battery without utilizing fail-safe features, you'll lose your variables program and your date will reset to around 1996, which can be a significant issue. Traditional architecture is available in many products. One advantage of this approach is its cost effectiveness, often found in lower cost products. The next architecture with Horner all-in-one controllers is their rechargeable battery design. This emerged due to the increasing use of processors tailored for mobile devices like phones and iPods, which rely on rechargeable batteries. As these became appealing for automation applications, including OCS, we adopted them alongside rechargeable batteries. In this setup, RAM stores runtime variables. Flash handles application storage. When power is disconnected, the power management chip allows the system to run on battery for a brief period. During this time, the CPU copies current registers and variable values from RAM to flash, taking about 100 milliseconds. ensures that RAM stores variables while flash retains their latest values when the system is powered down. Upon powering up, the reverse operation occurs, with the last values of variables copied from flash to RAM, allowing the system to resume. Now we have our rechargeable battery architecture for Horner OCS, commonly found in our mainstream products. One key distinction here: in contrast to the traditional architecture where losing the battery resets variables to zero, in this architecture, without preventative measures, variables revert to their last stored value from the most recent successful power down. The third architecture, next generation design, utilizes innovative RAM chips for variable management. This new RAM technology is retentive and includes two main types. The first is FRAM, which has limitations in speed and capacity. It has been employed in only one product due to these limitations. The second is MRAM, or magnetoresistive RAM. While slightly more expensive, it overcomes the speed and capacity limitations of FRAM. Additionally, it has significant advantage in not requiring a battery to maintain register values. The notable advantage of MRAM is that a small coin cell battery is only needed to maintain the calendar clock. If this battery were to fail a decade from now, the sole loss would be the current time and date. This approach will be adopted in most of our forthcoming products. We should note that we briefly mentioned FRAM, a type of retentive RAM with capacity and speed limitations. We have utilized it in the X5, why the X5 has a more limited register complement compared to an XL4, despite having a similar processor. Now that we've seen the memory's role and how it all fits together, let's look at the FailSafe features, beginning with backup and restore. This feature holds significant importance as it can be a lifesaver in the event of a battery problem, even if it arises 7 to 10 years after system deployment. A notable advantage of backup and restore is that it operates without the need for a memory card, contrary to a common misconception. So what does backup and restore accomplish? It copies crucial information to a secure location in flash memory. When a backup is performed, it duplicates the OCS application program's checksum. All variable and register values and all system settings configured is securely stored in flash memory, ready for retrieval when needed. The feature can be enabled from the system menu, or you can choose to activate it using system registers. Its primary purpose is to safeguard against potential future battery issues that may affect machines. However, it's important to note that it doesn't provide protection against flash memory corruption, which is an exceedingly rare occurrence. Therefore, backup and restore primarily addresses common machine issues. We'll look at a detailed demonstration of this later, but in essence, the goal is to have the system fully prepared for and ensure that everything is in working order. Step 1 is to set auto run equals on, and step 2 is to perform a backup. Performing these steps in order is critical. Otherwise, auto run equals off will be stored. In the case of traditional architecture, if you encounter a battery issue and have used backup and restore, it can prevent your program from being erased and preserves a functional set of register values. This allows you to continue running your system until you can replace the battery and restore your calendar clock. This is especially critical for traditional controllers since a battery failure can result in the loss of your program if you haven't utilized this feature. In the case of a rechargeable architecture, there are several advantages. Although in this scenario you won't lose your program when the battery fails, you might encounter issues with variables and registers. Nonetheless, it's still valuable to utilize this feature even with a rechargeable architecture. If you don't use these features with a traditional architecture, the primary consequence is that you'll lose your program or your variables will reset to zero. You'll encounter the issue of no user screen display and likely receive a phone call from support. In a rechargeable architecture, the main difference is that the system will revert to older registers and you'll lose your calendar clock. However, your program will remain intact. We'll start at a point at which the program is running the way we want. Everything we would normally set from the system menu is set the way as well, and we're running the application program that we want with the variables all with the proper value. So then we go to the system menu, go to FailSafe, and start by enabling Auto Run. Auto Run means that if we ever have to recover using FailSafe, we are going to recover and then go into run mode automatically. The next step is to perform a backup, which we do here from backup and restore data. This backup takes a copy of the checksum for the current application program and a copy of all the current things and a copy of the current value of all the variables and registers in the program and store all that to a safe area of flash. And then, if we ever have a battery problem in the future, we can recover from that by loading in this known set of good data, allowing the system to recover until the battery can be replaced, and the system can be fully brought up to 100%. But your program will be running with a known good set of data. So now that we performed these steps of enabling auto run and performing a backup, we're ready if we ever have a battery issue. Now we're going to illustrate how backup and restore can help you recover as well as possible in the future if you have a battery failure. So this unit does not have a battery, and that's how we're simulating the failure. We've made some adjustments to our parameters as they are not exactly the same as when we first started running the unit. So now we'll perform a power cycle with a bad battery or a missing battery, and we'll see what happens. So it's powering up and it says self-test failed. However, we did recover. So you'll notice that these values are not the same as when we powered down, but they do match the values when we performed the backup. And if we go to the system, you'll see the OK light is off. The OK light is off because we have a bad battery, but we are in run mode and we are operating. The other thing that has happened without a battery is that our calendar clock is not able to keep current time. So if we look at time and date, you'll see that we've gone back to the default time and date of January 1996. And every time we power cycle, we're going to go back to that day. So it's not perfect, however the system is running using a known good set of values, and we have recovered. Now we can fix the battery, set the clock and fully recover with some human intervention. The next fail-safe feature we'll discuss is auto load. Auto load serves to protect against flash issues, including rare flash corruption as well as accidental program deletion. This can happen if someone inadvertently deletes a program in Cscape, or more commonly due to a failed or aborted program download, leaving the controller without a valid program. Autoload, however, does require a memory card. These are readily available and affordable nowadays, and they offer additional useful features such as data locking. Autoload is activated when the OCS powers up and passes the battery and RAM tests, but finds no valid application program running. In this case, Autoload will search for a program named autoload.pgm on the memory card. If it's present, it will load and run it. This feature can be enabled from the system menu, just like backup and restore or using system registers. The setup steps are remarkably straightforward. Simply enable a couple of parameters in the system menu and you're good to go. It's a straightforward process, but we'll demonstrate it for you shortly. If you've enabled autoload, whether using a traditional or battery-backed architecture in any of our products, when the OCS powers up with a functional battery and RAM but lacks valid program, it will search for autoload.pgm, load it and run it. Importantly, there are no issues with the battery or RAM, so the calendar clock continues running smoothly and the variables remain intact. Conversely, if you haven't enabled autoload, your OCS will remain idle when it powers up without a valid application program until someone addresses the issue on site. Now we'll demonstrate this failsafe feature. It's important to note that while backup and restore, as shown earlier, is unquestionably the most crucial failsafe feature, autoload does serve a valuable purpose. It safeguards against situations where you might lose your program, such as during an interrupted download, perhaps due to a remote download over the internet with a sudden loss of cell connection. This can leave your controller without a valid program, and autoload steps in to automatically load a known good program at the next power cycle, ensuring recovery. Now we'll demonstrate how we set up autoload. Once again, we go to the system menu, and we have our application set up the way we want. Now autoload, unlike backup and restore, does require a remove card. So we have one here, it just happens to be empty. The next step is to go back to the FailSafe menu and make sure that autoload is enabled. We'll set that to yes. And after we load the program automatically, we are also going to want it to run automatically as well. Yes there also. So now we've made sure that we have a memory card and made sure that autoload and auto run are both set to yes. Now when we automatically load this program, if that eventuality ever happens, we have to have a program to load, and that program has to be named autoload.pgm. Now we could create that file from Cscape using the export to removable media feature, but the easiest thing to do is from the unit itself. Perform a make clone. So we've gone to the clone menu and we're going to make clone. And the process of creating a clone is going to create the PGM file that we need for autoload to work properly. Now we'll also create a clone.file, and for the purposes of autoload that won't be used. Because remember, in our scenario, we don't have a problem with registers or variables or system settings, we have a flash problem. So we aren't going to have to reload system settings and variables or register. All we need to reload is our program, which has become corrupted or invalid for whatever reason, most likely an aborted download for instance. So now we're set up properly, and we'll go ahead and simulate the failed download. Off screen, we'll perform a download. So the download is starting soon, and you'll see the impact on the screen of the controller. Now what we're going to do is we're going to interrupt that download. So this simulates maybe we're trying to download the unit over the internet through a cell modem and you lost your connection. And now you have issues. So this unit does not have a valid program. Now the way that we can recover from that is going to require a power cycle. So now we'll perform that. So we've reapplied power, and now we'll keep an eye on the diagnostic message. We have errors, corrupt user tables, and we're initializing our autoload and then run. We're loading from the memory card and we have fully recovered. If we go to the system menu, you will see both OK and run are on. So this had nothing to do with the battery. So our time and date and all that sort of thing is still fine. So this illustrates autoload, whose main goal is to store a valid known program should the unit ever power up with corrupted flash or with an invalid program because of an aborted download. So what you want to do, especially if you have a memory card, is you want to set both of them up. If you have a memory card, because that's required for autoload, just use them both. So in this next demonstration, we'll show you the proper steps to set them both up. Again, you need a memory card, but this will give you both backup and restore and autoload capability. So now that we've showed you individually how both backup and restore and autoload work, let's go through the process from start to finish for enabling everything. So we have the application where we want it, the program is loaded, and we have all the settings the way we want them. So we'll start from the system menu, and we're going to go to the FailSafe menu and start by enabling autoload. Now we're going to enable auto run. So as we recover, we will automatically go into run mode and then we'll perform a backup. Now in order for autoload to work, we need to make sure that we have a memory card installed and an autoload.pgm file. Remember, if we don't have a memory card, we can still use backup and restore, which will protect us from a battery issue. But if we do have a memory card, we might as well go the rest of the way and make sure that autoload works as well. So the easiest way to make sure autoload.pgm exists is to go ahead and make a clone, because the system is just the way we want it. So now we're done. So that's a rundown of how to use backup and restore as well as autoload. Now we'll look at cloning, which, as previously mentioned, is related to failsafe features but not a failsafe feature itself. Cloning allows system designers to duplicate the operational state of one of our all-in-one controllers onto an identical unit. This process is only effective when dealing with units that are exactly the same. For instance, cloning from an XL4 to another XL4 but not from an XL4 to an XL7. If you're an OEM or engaged in production, regular shipping units and have a reliable reference unit, cloning becomes a valuable tool. You create a clone from the reference unit, save it on a memory card alongside autoload.pgm, and use these files to load the clone onto blank units, ensuring consistent replication as you ship units. This functionality is not only beneficial for production but also for controller replacement scenarios. It's worth noting, if you have a security enabled in Cscape to safeguard your intellectual property, unauthorized users won't be able to load a clone without the appropriate authority. The system will prompt for a password, adding an additional layer of protection against unauthorized cloning and potential intellectual property theft. And once again, you can do cloning from system registers, even though it's a little less common, it's still possible. There are system bits available for that function. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, I'm not seeing any questions as yet, but the next webinar will be MQTT Sparkplug, which you can go to our website, to our webinar page, and the registration link will be there with all the details. I'll just give it another couple of seconds or so, see if anything comes in. Okay, well, I think we'll leave it there. Thanks for joining us, and we hope to see you again soon.